Okay, so today we're transitioning to the somatosensory system. So if you want, I have one more lecture on the visual system, on object recognition in the visual system, and that will be the advanced lecture on Friday. So that's an interesting lecture about, like, sort of higher, if you go up to the very top of the visual system, where you have sort of object recognition, how does that actually, how do we think that actually works? So I'll go over some experiments on that on Friday at 8 o'clock. Okay, so the plan today is to transition to the somatosensory system, and I spent a lot of time on the visual system. So we had Reichart detectors, center surround orientation, aperture problem, higher level pattern recognition, rotations, and so one of the reasons we spent so much time is if you look at a monkey brain, it's about a half visual. It's a little less than a human, but it's about a half visual. And so if you just sort of divide up the areas, it's about 1/8 auditory, 1/8 somatosensory, about 1/8 motor, and 1/8 limbic. Social, emotional, motivational. So the visual system is huge compared to these other systems because we live in the daytime. We have eyes, and so that's kind of the reason to focus on it. So we're going to talk about somatosensory. We're going to talk about the 1/8 of it that is somatosensory for the next week. So we won't spend as much time. There's also, given this kind of overall distribution of these systems, there's also less research on the somatosensory system compared to the visual system. So that's another factor to take into account. Now, all animals aren't like this. If you look at a bat, they have a giant auditory system, and the visual system is pretty shrunken. But there are even animals that mainly use the somatosensory system. So there's something called a duck-billed platypus. I don't know if you've ever seen one of those. It's kind of this strange thing, and it's got this big bill and a little tiny beady eye, and then it's an early mammal that lays eggs, has a long tail. So if you look at that animal, egg-laying mammal, it's a somatosensory animal. So you look at the auditory system and the visual system, they're tiny. And when it's hunting, so it swims underwater. When it's hunting, what it does is it closes its eyes and ears. It's just like, let's get rid of all the useless information, close the eyes and ears, and then it uses this giant bill, which has electrosensors and touch receptors to actually hunt. So it's possible to make a main somatosensory animal, but we're sort of mainly visual animals, in terms of the actual sort of overall distribution of, our different sensory systems. So I'll talk a little bit more about sort of different, sort of the evolution, when we talk about the receptive system, which is part of the auditory system. We'll come back to sort of differences between animals. But for now, let's just talk about differences between modalities. And so when we look at the visual system, when we talked about the receptors, what is the sort of basic pathway into the brain? And the basic pathway into the brain was we had this, photoreceptor, and then there was a bipolar cell, and then there was a ganglion cell. And the ganglion cell is what actually went into the to the brain, the retinal ganglion cell. So this was ganglion cell. So like the X and Y cells, those are the guys that went into the central nervous system. So when you look at the somatosensory system, it's quite different. It's sort of confusingly different. So in the somatosensory system, what happens is you have these cells called dorsal root ganglion cells. We talked about them back in the day in development. They come from, the neural tube rolls up, and then there's kind of little leftover stuff at the top called the neural crust. And so the tube seals, but there's this kind of like the lips of the tube are kind of left over, and they sort of like crawl down the side and form the dorsal root ganglion cells. So the way the somatosensory system works is like, here's the skin, and here's the dorsal root ganglion cell. And what happens is the receptor is actually just the end of the dorsal root ganglion cell. So these cells, like the retinal ganglion cells, have dendrites, and they're receiving synapses from amacrine cells and bipolar cells. But in this case, what happens is the receptor itself is the actual axon of the ganglion cell, and the ganglion cell doesn't have any dendrites. So it just goes in to the central nervous system. So here's, CNS down here. So it goes into the central nervous system. And so it's just basically an axon with no dendrites. And this little connection so it's just a long axon, and then one end of the axon is actually a specialized receptor, and we'll see there's a whole bunch of different kinds. So that's different. So when we talk about the auditory system, so this guy is dorsal root ganglion cell. There's a bunch of different types, so we'll talk about them. So if you look at the auditory system, you've got yet a confusingly different setup. So in the auditory system, what happens is you have these things called hair cells. They're not related to like head hair. So they're a specialized receptor cell type, and it doesn't have any axon. And then what happens is you've got a ganglion cell, and the ganglion cell has like a teeny little dendrite that receives a synapse. It's kind of like it's got a miniature tiny dendrite that just receives a synapse from the hair cell, and then that goes in. So that's yet a different system. So this guy is the cochlear ganglion cells. So cochlear ganglion cell, and then finally you got the olfactory system. There's also taste, but let's just talk about the olfactory system. So the olfactory system is kind of like the auditory system, is you have taste buds, which are specialized cells, and then you have a ganglion cell going to the taste bud. The olfactory system is yet different. So the olfactory system has a receptor cell like this, and it's a hair cell. Usually has one or two hairs on it, little cilia. That's why it's called hair. It's not like a head hair cell. But that receptor cell grows into the central nervous system. So where is this thing? This is in the olfactory epithelium. And that actually grows into the central nervous system and contacts the olfactory bulb. And we'll talk about that when we talk about the rest of the limbic system. So confusingly different sort of topology in these different systems. But what we want to talk about today is the somatosensory system. And so what we're going to talk about is all the different receptor types that you have in the somatosensory system. And the one thing that really, I try to make sort of analogies between different things in the different modalities. So one of the things that we'll see occurs in the somatosensory system, just like the visual system, is you have this difference between X-like sustained cells and Y-like transient cells. That sort of distinction appears again. But there's a couple, but there's one really big difference about the somatosensory system, sort of really zooming out compared to the visual system. And what that is that the range of different kinds of information that the somatosensory receptors are picking up is much greater than is the case in the visual system or the auditory system. So the visual system, you've got, photoreceptors, and you've got, red, green, blue cones, and you've got rods, but they're basically sort of about the same thing. They all hyperpolarize, and they've got, photopigments in it, and the way they work is all pretty much the same. And so the kind of information that comes in is kind of one kind of information coming in through the visual system. Same way with the auditory system, you got these hair cells, and these, we'll talk about the vestibular system, but if you just talk about the auditory part, they're all pretty much the same. When you look at the somatosensory system, it's just a bizarre collection of fundamentally different kinds of information. And so we'll make a big list of them and then hook them up to the spinal cord over here. So the first kind of main sort of class of receptors are called unencapsulated. So that must mean that they're not in a capsule. And so what are the encapsulated ones that we're contrasting with? Those would be a receptor that has some other cells associated with it, not neural cells, but some other sort of like physical support cells associated with them. But some of these receptors are just called unencapsulated, and what they just look like, if you look at them anatomically, they just look like a little wire. It's just a little wire going into the skin. But it's got a sensitive tip, a particularly sensitive tip, and there's a whole bunch of different kinds. And so one of the first kinds are heat receptors and cold receptors. Those are different from each other. So heat and cold receptors. And so every year I always talk about, where are the most cold receptors? And this has been heavily studied in the rat scrotum. There's a ton of them down there because the scrotum is supposed to keep things cold relative to the body. So there's a lot of heat receptors. That's where they've been studied heavily in the rat scrotum. But there's a difference between heat and cold. And if you have a friend, you can actually take a little warm or a cold probe, a little piece of plastic or metal that's warm or cool, and touch it to their back. And what you'll find is that on your back, there's not that, the receptors are kind of spread out compared to the scrotum. And so if you actually sort of touch different spots, the person will say, no, I can't feel that. And then you'll say, oh, I feel cold. So the receptors are spread out enough that you can actually find a place that doesn't have any heat or cold receptors in it. And so it's kind of like sort of on and off. You have sort of heat and cold. They adapt. So one cool experiment you can do at home is put your right hand in warm water and your left hand in sort of ice water for a while, and then grab something. And the one that's been in warm water, it will feel cool, and the one that was in the ice water, it will feel warm. So that they're all sort of adjustable, but they're distinct. There's a distinct sort of cold and heat receptor. So that's a kind of information. It's quite different from touch. You normally think of somatosensory system of response to touch. Then there's pain. Now, pain isn't all bad. If you don't have pain, you're in really deep doo-doo, because what will happen is you'll bite your tongue off or do all different bad things. And so it turns out, it sounds like a good plan to have no pain, because who wants pain? But it's really bad if there's something wrong with your pain receptors and you don't have pain, because it's absolutely critical for just making sure your body is not damaged. And if we look at the pain system, there's X-like pain, like sustained pain, and those guys are called C fibers. And then there's Y-like pain, transient pain, and those guys are called A delta fibers. The C and A, it comes from the conduction velocity because you can, if you get a nerve, you can measure how fast the impulses go through it, and there's different size axons, and the bigger ones conduct faster, and so the A delta fibers are bigger. So we have the same thing, sort of, you'd never think of that. Same thing like X and Y cells in the visual system. You've got these separate cells in the somatosensory system. Now, the interesting thing is they're not created by the circuitry in the retina. So, like, where does on and off come from, or where does X and Y come from? It comes from circuitry in this retinal ganglion cell layer that's taking a single signal that's sort of that's not sustained or transient, not X or Y, and generating an X and Y out of it. How does this work? It's different. The actual receptor does it. So the actual receptor essentially determines, whether it's kind of like a sustained thing or a transient thing. But that's an important, when you think about it, it's kind of like the nervous system abstractly knows that it needs to differentiate these sensory signals into multiple streams, and by hook or by crook, it's going to do it. So in the retina, it does it with some circuitry in the amacrine cells. Here, it does it with the actual receptor itself. So that means it's a sort of a deep structural kind of need of the nervous system to make these, sort of like signal and derivative of the signal kind of pathways. And so that happens in pain. These guys are, as you'd expect, these guys are small, parvo, and these guys are large. The transient ones are more large. Now, until recently, it was, pain but no pleasure. But now it turns out there's another set of receptors that specifically respond to slow, pleasurable stroking. And so these are specific receptors that respond to like sort of light touch that's moving relatively slow, like 1 centimeter per second. So like something like about like that. And so the receptor, it won't respond if you do that. So it just specifically responds to this kind of grooming, kind of sort of pleasurable grooming feelings, like slow stroking. So there's actually sort of pleasure receptors in there too. Obviously, completely different than heat and cold and pain. But then we have a whole bunch of touch receptors. So these are the ones that you would normally think of, and these guys are encapsulated in general, which means that they've got some related non-neural cells around them that are around this little squiggly end of the ganglion cell. And there's 5 different ones we'll talk about that are picking up different kinds of information. And so there's superficial ones that are meaning like near the surface of the skin. So the superficial ones are German. So there's a thing called Merkel discs. And then Meissner's corpuscles. Okay. And the Merkel discs are the sustained ones. So these guys are sustained. And these guys are transient. So Y-like. Now, one of the things, if you read the literature in the somatosensory system, they use a different terminology. Their terminology for, so in the visual system we said sustained, and that was also kind of like X cells, and that was these also sort of parvo, small ones, parvo. And so if you go in the somatosensory system, instead, they call these guys slowly adapting. That's a synonym, basically. That makes sense, slowly adapting, meaning that if you do a stimulus, they still give you a response after a while instead of adapting and stopping responding. So that's the somatosensory name for that. And the transient ones, which we had in the visual system as, Y cells and magno, they're bigger cells. Those guys are called rapidly adapting. So the idea is, you present a stimulus and then very quickly the neuron becomes insensitive to the stimulus. So, so they wouldn't call these sustained. They would call Merkel discs slowly adapting, if you actually read the literature. So those are the superficial ones, and then there's some deeper ones. They're just situated deeper in the skin, and those guys are Italian. There's the Ruffini endings. There we go, Ruffini, and then there's Pacinian corpuscles. Pacinian corpuscles. And these tend to be a little deeper in the skin. So once again, these guys are sustained. You have some of these in your joints, for instance, and these guys are transient. The Pacinian corpuscles are really super transient. So they can actually follow very high rates, and just so if a car comes by with the giant 1,000-watt speaker system, and you feel that these Pacinian corpuscles can give you a spike for every note, every movement of the actual speaker. So they can follow like a 200 hertz signal and spike exactly on 200 impulses. So there's a lot of them in your gut, like when you're passing gas, the little bump, bump, bump as the gas comes out. These guys are telling you it's coming out. They can actually pick up vibrations, and you have a lot of them in your finger, deep in your fingers. And so if you touch a surface, you can quite easily pick up little vibrations, like say touch a railroad track as the train is coming. You can feel those little vibrations, the little rapid vibrations. That's the Pacinian corpuscles. And what they look like is they look like a little miniature onion like that. They're all sort of wrapped up like that, and then the axon comes in, like this axon comes in like that, and sort of like goes right in the middle. And this is a case where the transient property is actually generated by this little onion. So enterprising neuroscientists have peeled the onion off and just gotten the axon out of there. The axon itself is not transient. So the axon is not transient. So this transient property of responding very well to an impulse comes from the little onion, the physical onion. So like I said, by hook or by crook, we're going to make something that sort of is more transient, something that's more sustained in its response. So these are bigger, tend to be bigger axons also, the transient ones. And then finally, there's hair follicle receptors. And so what are these? These are basically, if this is your skin, there's like a little depression in the skin, and then you got the little hair coming out of it. There's a hair coming out. And then you've got the end of the ganglion cell, which comes and kind of wraps it around the bottom of the hair. And I always say, you can, if you want to feel just one neuron, just find a separate hair like this, and just want to tweak. Let's just tweak one ganglion, literally one ganglion cell. You can actually just stimulate just a single ganglion cell, which you can actually easily detect. Now, if you know about hairs, if you rip it out, what happens? Well, it comes back. So why does it come back? Well, if you rip out the hair, you'll snap off the end of the ganglion cell, and then the ganglion cell knows how to tell the skin to make a new hair. So the ganglion cell won't die. It'll just say I need a new hair, and so it will send out some signals so that a new hair is generated, and then when a new hair is generated, it will attach up to it. And if you've ever tried to remove hairs, you know that, they grow back. And so how do you do like serious hair removal? You got to like laser something in there so it causes a little scar so that when the ganglion cell tries to tell it to make another hair, there's nobody home. So the whole system is quite good at sort of putting itself back together. So you add a different kind of information. Now, if you look at something like a rat has what are called vibrissae, and vibrissae are different they're like hairs, but they're different than hairs in that they have actual muscles associated with them. And so the rat vibrissae system is this super high-tech touch system. So it's got like this array of like 25 vibrissae out there. And if you look at a rat in slow motion, sort of like hold a rat underneath and look at it in slow motion, what it's doing is breathing quite rapidly, like about 7 times a second. But then there's a sweep of the vibrissae, so it's going like, and it's sweeping the vibrissae over objects, and it can sort of detect the shape, of objects with these muscle-powered hairs, basically. Our, beard hairs are not like that. They just sort of sit there, not as good. But that's basically a modified hair follicle receptor. So again, it's quite different kind of information because it's got something sticking out of the end. It's picking up completely different information from heat, cold, pain, stroking, and various kinds of touch. But then there's another whole set of receptors of muscle receptors. So these muscle receptors are giving yet different categories of information. So the muscle receptors, so the first type are called stretch receptors. And so how do you actually tell where your body is in space? So like, if I'm doing something, how do I tell? Like, I can look at where my hand is, but if I close my eyes, I have a feeling like I got my hands like somewhere in front of my face, and now it's sort of touching my nose. How do you do that? You actually mainly do that by monitoring the length of your muscles. That's basically how you tell where different parts of your body are. So because the length of the muscle is going to determine where each body part is. It gets a little complicated because you got like multiple muscles that you have to take into consideration, but that's basically the information how you figure out where your different body parts are. And so these guys, and they're called stretch receptors because they don't respond to slack. So they only respond there's only on. They respond to stretching the receptor, but if you slacken the receptor, there's no response. So there's no off stretch receptors. But they're usually just called stretch receptors, or they're called muscle spindles. And we'll talk about them more next time. So there's type, and they've got like hard to remember names. So the type 2 muscle spindle. So the type 2 muscle spindle is sustained. So these guys are, slowly adapting. And then the type 1A, this was yet a different categorization of the speed of conduction. So the type 1A they're 1 because they're faster conduction. These guys are another muscle spindle, and these guys are much more transient. So these guys are, transient or rapidly adapting. So there's those kinds of muscle receptors, but then there's another completely different receptor, which is called type 1B. It's Roman numeral 1B. And these are called the Golgi tendon organs. And there's something about the juxtaposition of tendon and organ that somehow it's like, you don't expect those two words to go together, tendon, organ. And so what these things are, if you look at a muscle, like the muscle body is down here like that, and then there's a tendon, and then it attaches up to the bone here. So this is the bone here. And so the Golgi tendon organ, this end of the ganglion cell just comes along and just wraps around the tendon. And so what are these picking up? Completely different. They're picking up the force. So they give a signal that determines how much force there is. And so force, so that you can see force is going to be completely different than length. So you can imagine like your muscle, it could be up here or down here, but if it's here at a single position of length, you can put different amounts of force on it. And you got to know how much force you're applying also. So that's the kind of orthogonal, sort of a uncorrelated piece of information about your somatosensory system. How much force is the muscle applying, and as opposed to what is the length of the muscle. So you can see there's this giant array of completely different, fundamentally different kinds of information. It's quite different than the visual system. So you've already got like a whole bunch of different streams. And so what do? Well, they go into the spinal cord. And so they all go in. So let's draw like a gigantic spinal cord here. I need a little space for the muscle. So here's a nice big spinal cord. So it's the cross section of the spinal cord. So here's the spinal cord sort of going up to the brain, that direction. Okay, so if we look at our spinal cord, here's the ventricle. So that was the original ventricle of the neural tube. And there's 4 parts of the spinal cord. So the spinal cord is, like the rest of the brain, like the left. It's behind the pons midbrain junction, so the left side goes to the left body. And it's generally got sort of a sensory part on the top, which is called the dorsal horn. So this guy's the dorsal horn, and then it's got a motor part on the bottom, which is called the ventral horn. So this is, the dorsal horn sensory, and this is the ventral meaning stomach. So this is the stomach side, horn motor. So like in the case of polio, for instance, polio damages the ventral horn, sort of interrupts motor movements. Okay, so that's for just half of the body. So here's the other half, and then here's the final dorsal horn on this side. Okay, so how do the muscles? How do you actually sort of move your muscles? So the way that works is, here's a muscle. And so what happens is the motor neurons just actually synapse onto the muscle. So if you have a motor neuron here, it's a big neuron sitting there. It has an axon that comes out, and it punctures out of the spinal cord. It's a different hole than this one. There's a hole here where the dorsal root ganglia come in, but the motor neurons come out of a different part of the underside of the spinal cord. And so that axon comes out, and then it just synapses on the muscle. It's actually a synapse. It's a gigantic, humongous synapse called an end plate. So this is called the end plate. And if you look in the central nervous system, you have like an axon coming along, and then you get a little synaptic bouton that sort of sticks to a dendrite. That synaptic bouton might release like one vesicle. But the end plate is just like a humongous synapse, might release 200 vesicles. And what's the goal? Well, the goal is to cause a spike. So here's a little spike. It's to cause a spike to go across the muscle. So that's how you actually move your muscles. You literally cause spikes spreading across the muscles. So one of the things about the somatosensory system, like I said, it's not as well studied. Well, it's also harder to study. And what is the reason? Well, what's the output of the somatosensory system, the motor system in particular? If we sort of I slightly changed from somatosensory to motor. But what is the output of it? Well, it's all these spikes in the muscles, but that's actually pretty hard to record. You can record it, and so one way of recording it is you just get a fine syringe needle like that, and then you get a really fine wire and just take this fine wire and fish it down there and bend it up like that, so you got a little hook on it. And then you can inject that into a muscle. It doesn't hurt a bit. You inject that into a muscle and then fish out the syringe needle, fish out the syringe needle, and you got like a little wire going down into your muscle. Then you hook that up to an amplifier, and then when somebody does that, you hear this like, you can hear like the actual spikes coming out of the motor neuron. That's called, EMG, electromyography. So that's how you really find out what is the actual output of the motor system. It's a complicated set of little spikes going out to all these different muscles to sort of make you do some complicated motion. So that's eventually how the output gets out of there. But let's go back to the input. And so all of these different receptor types. So here's a dorsal root ganglion right here. So it's a little sort of swelling like that. And so it has, a dorsal root ganglion cell in it, and it's got this little shrunken little connector, and then it's got the actual axon that's going into the central nervous system. And what's the other end of the axon? Well, it's all these guys. There's a whole bunch of different ones, right? So all these guys actually have their own dorsal root ganglion cells, hair follicle, that are going in. So what happens when they go in? Well, this is something that you generally don't get in a neuroanatomy class unless you're like hardcore in a neuroanatomy class. So there was this guy named Rexed, R-E-X-E-D, and so he looked at the spinal cord. If you look at the spinal cord, it just looks like, the dorsal horn just looks like whatever. But he found layers in it, and so he distinguished 9 layers in the spinal cord. And like I said, if you looked at this, you'd say like, wow, I cannot see any layers at all. But it's a little bit like the geniculate. So you've got you have these multiple layers in the spinal cord like this. Let's make that one a little bit bigger. And when people looked at this in detail, they could see that actually the different kinds of information was going to different layers, and they number them. They number them starting from the top, so that's layer 1 in Roman numerals. So this is a guy Rexed, and there's 3, 4, 5, 6. Oops, 6, and then 7, layer 7, it's not really a layer, is kind of it's like the reticular formation of the spinal cord. So what is, we haven't talked about the reticular formation, but if you look up in the brainstem, like in the medulla, the middle of the medulla, the middle bottom of the medulla, has a bunch of really big cells in it. That's why it's reticular, because it looks like a mesh or a net. And if you follow the spinal cord up into the medulla, basically the reticular formation up in the medulla is the same as this middle part of the spinal cord. And so it's kind of like the coordinating part of the spinal cord that essentially communicates. So the spinal cord is quite smart. It actually can talk to different parts of the spinal cord without involving the brain. So one part of the spinal cord, say controlling a leg, can send a message to another part of the spinal cord controlling the arm, and the brain, who knows what the brain is doing? It can talk to different parts of itself, and this is very important for coordinating movements. So the spinal cord, normally you think of like, well, the spinal cord isn't cognitive, but it's actually doing complicated things like sort of coordinating how your foot and hand moves, or if you move your foot, that changes your balance. You need to sort of move a hand to sort of cancel that out. It's doing pretty high level stuff because it communicates back and forth to itself. So there's some cell here might, pick up some information from the spinal cord and then go into the white matter and then go to some other part of the here, let's make that in perspective. So it's it's going to go to some other part of the there we go, other part of the spinal cord and connect up to a cell, somewhere else, and send information back and forth. If you want to read about that, probably don't, but those are called propriospinal connections. So like connections between different parts of the spinal cord. So the spinal cord is quite smart. It's thin, but there's a lot of it. So it's got a lot of parts in it. Okay, so let's go back to sending in all these axons here. So if we look at the very top layer of the spinal cord, that's where the A delta, so that's the fast pain, goes to. And then the C fibers come under that. So in layer 2, so that's very specific lamination, just like the geniculate. It's kind of, you can sort of think of it like the layers in the geniculate, like different categories of information are coming in. They all have maps in them. So there's maps in the spinal cord. It's obviously mapped to different parts of the body, but at the same time, at each point in the map, there's multiple streams of information. And so some of the Meissner's corpuscles are over here. So these are, MS for Meissner's. They go to layer 3, and then we have a lot of Merkel discs in layer 4. So those, as you can see, there's a distinction between the transient and the sustained ones, kind of like there is in the geniculate. And then we've got some Pacinian corpuscles, some P down over here. You don't have to remember this. We've got some heat and cold guys over here. There's they're up with the pain. That kind of makes sense. And then there's some more Pacinian corpuscles. Some more P's that are kind of like over here. And then when we get to layer 6, that's where we have the type 2 and the Golgi tendon organs and the type 1A. So the muscle receptors, they're in a different layer. And I've set up the layers pretty much the same way as I set up the list of all the different receptors. And so if we just look at one of these guys, let's put it in a different color. Let's put it in blue. Okay, so one of these guys comes in like this. So what do? Well, let's take one that goes to, let's say it was a 1A, one of the 1A ones. So here's a 1A ganglion cell. So it comes in and it goes down and it synapses on a 1A cell. So this is a sensory part of the spinal cord. But these are enterprising cells, so they actually have another axon that comes down and sometimes can synapse directly onto a motor neuron. And that's the reflex arc, where if you tap your knee, it rapidly stretches your thigh muscle and activates these very transient 1A stretch receptors and then causes the muscle to contract. But then there's additional pathways. So another wire will come off, and then it will essentially go up toward the brain. And so that's a long friggin' axon. So you got a ganglion cell somewhere down in your spinal cord. It comes into the top of your spinal cord and then sends a branch off that goes all the way up to your brain and synapses in the it's all the same axon. Now, of course, there's going to be other neurons that are in this layer 6, and those guys are also going to go up, go up and synapse. So there's multiple pathways. So they might receive some input from that same axon, do some processing here, and send that up. So it's, the spinal cord is a big thing. So lots of parts in it. So we didn't finish the layers. So here's where the motor neurons are kind of sort of clustered into little clusters related to different muscles. And those are sort of somewhat arbitrarily called layer 9. So this is 1x. That's layer 9. And then the space in between is called layer 8. And then the reticular formation of the spinal cord, that's, this part here that sort of does this is the reticular formation of the spinal cord. That's quote unquote layer 7. Doesn't look like a layer. These actually look like layers. Okay, so that's the basic sort of layout of the somatosensory receptors and streams that are coming into the brain. Very different than the visual system, because the streams are a lot more different from each other than they are in the visual system. Here's the question.
Yeah, isn't it something about that the heat and the pain is kind of the same, like an example for a chili? Or is it just because it's in the same layer?
So like chili, so I like to eat really super hot food, and so one of the things about you have salty, and you got sweet, and you got sour, and you got all these different smells, and then you got pain. It's just another it's another flavor element, a little bit of pain. And so, like, if you eat a very spicy thing, that's going to activate your pain receptors in your tongue. But it makes for a fuller experience. You can have a little sort of just spicy flavor, aromatic flavor, and then some pain mixed in there. So there is a distinction clearly between pain, versus heat and cold. So heat is not the same as spicy heat. Spicy heat is actually pain. So so that's our.
Is there an explanation why it also feels warm?
If you eat really spicy food, why does your tongue feel warm? Maybe.
Yeah.
Well, it's sort of, there's a little bit of a warmth element, but if you eat something really spicy and then drink some water, you'll say, like, no, that's definitely pain. It's definitely pain. It's known that capsaicin specifically binds to pain detectors. So like that's the chemical component of like a hot pepper, and that it's oil soluble. The capsaicin is, and so that's why, like alcohol so water doesn't wash it out. You need something that will dissolve an oily substance. But it definitely specifically goes to the pain receptors and turns them on. These guys, like at this end, it's touching the end of the ganglion cell that has a pain cell. It's got a specific receptor in there, and how does it work? Well, normally it's supposed to indicate the potentiality of tissue damage. So, like, what is pain for? Well, it's designed to tell you, whoa, you're getting too hard there. You're gonna get some damage. But think about that. There's a whole range of pain. There's no pain, and then there's a little bit of pain, getting kind of dangerous, and then pretty intense pain, and then actually this is the point where you start getting tissue damage. So one of the things about pain that I often mention is pain's not all bad. First of all, it's not all bad because you got to keep all parts of your body intact, and it really helps with that. But also, in this range of pain, before you have achieved any tissue damage, there's a lot of other cognitive uses of pain. And an example is like if you hang from a bar. If you hang from a bar, you'll compress your fingers enough to activate nociceptors. So these guys are called, nociceptor, like pain receptors. So these guys are nociceptors. So you'll if you hang from a bar, you'll get pain, a little bit of pain. It's not enough to really damage your fingers, but it's pain. And so pain can also be used for. So if you're supporting yourself by your hands and you got a little bit of pain there, then you kind of know, like, yeah, I'm safe. I'm hanging on there. I'm getting a little pain. Pain is good. A moderate amount of pain is good. And I'm thinking, like, the example I always give is if I'm going to drill something on a drill press and I'm too lazy to clamp it in place, I just hang on to it really hard up to the point where I start to get a little pain out of my finger. Not excruciating, but just a little pain, so that I know I'm really hanging on to it really hard. And so pain, there's a whole range of pain where it has these other sort of cognitive elements about sort of, safety, or, are you actually sort of still hanging on to that branch, So it's not just sort of dolorousness and sort of not all bad. Or like, hot food. It's like, it's a little pain. It's just expanding the experience to, sort of multiple different sensory input channels. So pain is a very interesting topic, especially, why can you just shut it off sometimes? So if you ask, if you go to the ER and somebody comes in and they've, done something really bad, got in a car accident or something, maybe about like 30% of the time, 40% of the time, if you ask them, are you in pain? They'll say no. Actually, like, something really bad has happened. It's definitely stimulating a gazillion nociceptors. And maybe about a third of the time, people will say, no, I'm actually not in pain. Even though, like, I've clearly got something that's done. I mean, I was surprisingly not in very much pain when I broke all these bones in my shoulder. I didn't even realize there were any broken bones. It was a little sore, I could sort of feel it was sore, but I didn't realize, how much damage was there. So that's an interesting thing. And one question is, why can't we do that all the time? It's like, my back's bothering me. Just turn it off now. I'm just ignoring it. It's very hard to sort of consciously make it go away. But definitely there's mechanisms in there that can just completely shut it off, even though the giant signal is coming through. And the best example of that is if you injure yourself when you're doing something and you're concentrating on doing it. So if you're drilling something or sawing something, it's very common when somebody's doing that they will not detect severe tissue damage that occurred because they're concentrating on sort of like, doing something. And so you can just completely flick off the pain pathway. So it's sort of an interesting system. We would, of course, like to find ways of doing that when you have some kind of chronic pain. And chronic pain, especially when inflammation gets involved, is a real nasty. So, but yes, so there's a lot of sort of, there's a lot of interest in pain. Yes. Oh, definitely. So, like you could put like a capsaicin patch on, which is like directly activating pain receptors. But if you put that on, it can sort of adapt some of them and kind of slow things down. Other pain things like lidocaine will just block these guys, and so then there's just no signal. If you inject some lidocaine, it just shuts off neural transmission, and you don't feel anything. But you probably have heard of phantom pain, where people have, if you get some severe damage, sometimes you can get pain that seems to be coming from something that's missing. And obviously that's a serious problem. Initially, people thought this was all some kind of cognitive thing, but now, in some cases, what happens is if you've damaged your limb, there's actually these ganglion cells that are still there. They're still going to, these layers up here. And so sometimes you can just do like an injection of lidocaine into the damaged spot, and that will stop the stop the phantom limb pain. So in that case, it's not phantom. It's actually coming from these remaining ganglion cells that are now no longer properly innervated where they're supposed to go, and they're getting inappropriately activated. Other times you get true phantom limb pain where you can't track it down to any pain input, and somehow there's just some kind of central support for the pain that just keeps it going without any sensory input coming in.
So when something goes wrong and people experience pain by stroking,
Oh yeah.
and experience that as pain, is that some?
Yeah, so that's an interesting question. Like, so people can get something called causalgia, which is this situation where even pleasurable, like very light touches can somehow strongly activate the pain system and cause like excruciating pain just from like a light touch. And so in that case, we know that there's involvement of the autonomic nervous system. So the autonomic nervous system can participate in causing swelling. And so we know in that case sometimes there's some kind of feedback loop that's happening where the autonomic nervous system is somehow causing the pain receptors to be inappropriately activated. And so that's another nasty, like you can get these like really extreme pain from things that are definitely not painful. So yeah. So it's a pain. It's always, because of its kind of emotional, centralness. Pain is a very interesting topic. Pain and attention. How attention can modulate pain. But yes, there are these kinds of cellular mechanisms in the spinal cord that can cause chronic pain, and they have, if you want to Google it, there are these things called inflammasomes. So there's like some is like a body. So inflammatory bodies that can actually get turned on in the actual neurons in the spinal cord, and then just wreak havoc with sort of the normal balance of pain. Okay. Yeah. The other one last story I often would told. I used to have an apartment, and the hot water was too hot, like it would boil in the pipes. I'd turn on the thing, and I'd get steam out of the hot water, and so I'd always forget, and I'd turn on the thing, stick my hand in there, and I clearly remember this one time where I pulled my hand back really quickly, but I didn't feel the C fiber pain. So the A delta pain went into the spinal cord. I said, get it out of there. I pulled it out of there, but it didn't hurt yet. And then with a delay of about a quarter of a second, I felt like, yow! That was like the temporally delayed C fibers coming in with they're very fine fibers. And so it took a long time for the signal to get all the way up to the brain. But the spinal cord knew. It immediately went back out and get your hand out of there. Okay, well, I think I went enough over about pain, but the take-home message is this giant array of completely different kinds of information coming in to the somatosensory system, and then how it gets up to the brain through all these streams.